So welcome to the ISSP theory seminar. So today I'm giving a talk. So today I'd like to talk about the Drude weights and F sample for linear and nonlinear conductivities. Actually, I have given talks on same or similar topics actually already many times, but I think not at ISSP. So I chose this subject for today's theory seminar. So feel free to interrupt if you have question or comment. But I am now recording the talk, and probably we will post this video to YouTube or somewhere. So open to public. So please, just remember that. Okay. So first, very rough motivation. So of course, conductivity is one of the most basic. Basic property of the material, and for many years, most of the studies have focused on the linear conductivity. That is, you apply the electric field, then current is generated, and this proportionality coefficient is nothing but conductivity or linear conductivity. But of course, current response is not generally just linear to electric field. So you can have a second order coefficient, third order coefficient, and so on. And these coefficients are so-called nonlinear conductivity. And of course, nonlinear effects has been there for a long time. But recently, these nonlinear conductivities of a lot of interest recently. There are various reasons, I think. One reason is that progressing experimental technology techniques enabled observation of these nonlinear effects more precisely. For example, now we have strong laser beam source. Then if you shine material with a laser beam, for example, then you are applying a very strong electric field, and you can observe nonlinear effects more clearly these days. And of course, on theoretical side, we have better understanding, especially computational techniques. So now these nonlinear conductivity or nonlinear responses are studied very vigorously. And just as an example, for example, recently there's a lot of discussion on so-called shift current, which produces basically second order conductivity. That is current proportional to electric field squared. And this can be also useful for applications because, for example, if you have some material and shine the laser or some electromagnetic wave into the material, then of course light or electromagnetic wave means that the electric field is oscillating. So if you just consider linear effect, then electric field is oscillating. So the current response is also oscillating. So if you take a long-term average, then linear current just vanishes. But if you have such a second order effect, electric field is oscillating, so changes sign positive to negative. But if you have this effect, then you have current induced in one particular direction. So even after taking long-term average, you can produce the current. So if you have this second order effect, then this material can work like a photovoltaic cell. So of course, we already have photovoltaic cells because of different mechanism, but this can give alternative mechanism for photovoltaic effect. So this could be useful. But in this talk, I'm not going to discuss particular material or any particular nonlinear effects such as this, but I want to develop the formulation of nonlinear response and nonlinear conductivity so that hopefully those formulations will be useful or provide foundations to study this kind of interesting phenomenon. Okay, so in this talk, I want to derive some general constraints on nonlinear conductivities. In particular, derive two kinds of general constraints. One is nonlinear F-sample, and the other is so-called generalization of so-called conformula for Drude weights. And I'm going to derive these two constraints in a kind of unified formulation. And there are a lot of references. So if you are interested, I can give you the list. But in particular, my talk will be based on these two papers a few years ago and a more recent paper which just appeared in ISSP a few months ago. Okay, so first, I'd like to discuss the Drude weight and so-called conformula for Drude weight. And even though I want to, my talk is primarily on nonlinear conductivity and nonlinear Drude weight. But first, let us discuss linear Drude weight or Drude weight appearing in linear conductivity. So again, in linear response theory, the current is induced proportionally to the applied electric field. And in general, we can consider wave number and frequency of the applied electric field. And in linear response theory, the induced current should have the same wave number and frequency as the applied electric field. So then this proportionality coefficient, that is nothing but the conductivity, is also characterized by frequency and wave number. But in many applications, we can focus on zero wave vector because even if you shine the light has finite wavelengths, but usually the wavelength is much, much bigger than the microscopic length scale, such as lattice constant, interatomic distance. So at least as a first approximation, you can regard this wavelength as infinite, which corresponds to taking wave number as zero. In other words, I want to focus on the response of the current to the uniform electric field, so spatially uniform electric fields. But still, it can have frequency there. Okay. Now, this conductivity is just a function of frequency omega. Then generally, this conductivity as a function of frequency can have this pole at zero frequency, plus some regular function of omega. And this coefficient of this singular part, 1 over omega singularity, is nothing but so-called Drude weight. And this Drude weight is important because this can be used to distinguish conductor from insulator. Or more precisely speaking, if this Drude weight is non-zero, or actually it has to be positive if non-zero, the system is perfect conductor. And if this D is zero, then the material, the system is insulator. So yeah, of course, this is in some ideal limit, like if you can compute this AC conductivity for very idealized model, like a Hubbard model or something, then you might get it. But in more realistic system, this delta function, like a singularity, can be broadened by coupling to phonon and so on. But in this talk, I want to focus on idealized model. Then, in principle, in conductor, you can identify this kind of singularity as zero frequency. And so this concept was already introduced in seminal paper by Walter Kohn back in 1964. That's almost 60 years ago. Yeah. Okay. So yeah, I want to study the response of the system to uniform electric field. Then to study this kind of problem, actually, it's useful, at least as a theoretical Gedanken experiment, useful to introduce this kind of geometry. That is, so let's say, yeah, I have some system, this is x direction. Then we can impose periodic boundary condition in x direction. Then topologically, such a system with periodic boundary condition is equivalent to torus or annulus like this. So if you go around the system, if you move to some length to x direction, you come back to the original function. Topologically, it's like annulus or torus. And then I can introduce a magnetic flux inside this thing. So this empty part, you introduce magnetic flux. Then, so this is very well-known setting in quantum mechanics, because if magnetic flux is concentrated in this empty part, then the actual system is this colored region. So let's say electrons are moving around in this colored region. Then electrons do not touch this magnetic field or magnetic flux. Then in classical mechanics, this magnetic flux should not have any effect on motion of electrons. But in quantum mechanics, you need to represent this magnetic flux in terms of vector potential. Then vector potential is non-zero even in this colored region. And yeah, it's a famous story, but in the presence of vector potential, when particle moves like this way to counterclockwise, or particle move to clockwise and meet at the same point, they acquire different phase, quantum mechanical phase. And that phase difference is proportional to this flux. So even though this magnetic flux does not touch electrons directly, the quantum mechanical particle motion are generally affected by this flux. This is called Aharonov-Bohm effect. But actually, phase difference is given by this flux. So if this flux is 2 pi or integral multiple of this 2 pi, then phase difference is 2 pi or 4 pi, and you cannot distinguish phase difference to 2 pi from phase difference 0. So that means that this Aharonov-Bohm effect is absent when this flux is 2 pi or its integral multiple. And yeah, I have implicitly chosen units so that h bar equals 1 equals 1. So in that case, the Aharonov-Bohm effect vanishes when flux is 2 pi. But in more standard unit, the Aharonov-Bohm effect vanishes when the flux inside this link is h over e, which is this particular value. So often we call this as a unit flux quantum, but this is twice the unit flux quantum commonly used in superconductor study, because in superconductor, the particle entity which carries a current is Kuba pair, which has charge 2e. But in this discussion, we use electron charge, so the unit flux quantum for our purpose is given. But if you take this unit, which is convenient for theories, then this unit flux quantum phi 0 is just 2. Then it's often useful to consider adiabatic change of the Hamiltonian and the spectrum, and also adiabatic evolution of the states by changing this Aron-Bohm flux from 0 to, let's say, 2 pi. Then, of course, well, in quantum mechanics, as I said, because of the Aron-Bohm effect, even though this magnetic flux does not touch particles directly, the particle motions are affected by this Aron-Bohm flux, which means that, for example, the spectrum of Hamiltonian also depends on this flux. This is nothing but one appearance of Aron-Bohm effect. So if you change the flux, then these energy levels change, generally speaking. But if flux reaches this flux quantum 2 pi, then, as I said, you cannot detect this phase difference, which means that this spectrum of Hamiltonian at flux 2 pi must be identical to spectrum of Hamiltonian at 0 flux. So this corresponds to the disappearance of Aron-Bohm effect at this particular flux. So naively, you might think, okay, so Hamiltonian must be equivalent because the spectra are the same. But nevertheless, if you write down the Hamiltonian, then clearly the Hamiltonian here is different from Hamiltonian there, because here you have non-zero flux, that means that you have non-zero vector potential. But here you have zero flux, so zero vector potential. So if you write down the Hamiltonian explicitly, Hamiltonian here is clearly different from Hamiltonian there. But still, spectrum is identical. And also, as I said, physically, you cannot use, as long as you measure whatever quantity in colored region, then electrons cannot know if they have zero flux inside or 2 pi flux inside. So physically, these two limits must be equivalent, although Hamiltonian are different. And this equivalence.
Sorry.
Yes. Yeah, sure.
So I wonder if we start with the ground state of phi for 0 and we do it adiabatic.
Yeah.
Would it also land on the ground state of phi equals to pi?
That's not necessarily the case. That's an important point. Yeah, of course, sometimes you can come back to this original ground state, but sometimes you do not. And yeah, sometimes
there are level crossings.
So yeah, but for example, yeah, so if this state ends up in excited state here, which means that somewhere you have to have a level crossing. And generically, you might expect, okay, so there must be level repulsion, and you should fall back to the ground state. But sometimes if you have, let's say, translation invariant system, then at the crossing, they have different momentum eigenvalue. Then this momentum conservation can protect level repulsion. So in that case, sometimes this translation invariance enforces this ground state to evolve into one of the ground states.
Yeah, but you are discussing melodic systems, even in the same subspace of the wave number, that there are many exciting states. So therefore, the level crossing usually generally true.
Yeah, that's also related to the point I want to make at the end. But yeah, you're right. But in metallic system, yeah, one point is that often because of momentum conservation, you cannot really come back to this original state. That's one constraint. But Snesu-san is of course right that even within the same momentum sector, there are a lot of states. Within that, generically, you must expect some level recursion, yes. But still, eventually, when you want to discuss the transport property of the material, this adiabatic process in the strict sense may not be appropriate. So we may need to discuss the different limit. That's point I will come up with. Yeah, thanks for the comment. Yeah. So okay, so the Hamiltonians are different, but physically, if you cannot really distinguish this system and this system, as long as you can measure whatever within the color region. So this equivalence is actually understood in terms of a particular type of gauge transformation. So at 0 flux, you have 0 vector potential, but at 2 pi flux, you have non-zero vector potential. But these two different configurations of vector potential represent the same physical station, at least within the colored region. And that can be seen by doing the gauge transformation. And in fact, in our problem, this colored region is topologically non-trivial, so annulus or torus. And corresponding gauge transformation is also topologically non-trivial. So the answer is that the Hamiltonian at 2 pi flux is the gauge transformation of Hamiltonian at 0 flux. And we can even write down the gauge transformation operator explicitly. But this gauge transformation is topologically non-trivial in the sense that, as you know, the gauge transformation generally is phase change of wave function depending on the location. And in our particular case, this phase factor should increase as you go to larger x coordinate. But if you go around the system once, x increases from 0 to Lx. So in this process, this phase factor should increase from 0 to 2 pi. Then in more trivial gauge transformation, this phase factor is single valued function of the location. But in the topologically non-trivial space, like annulus or torus, this phase factor can be multi-valued because you go around the system once and you come back to the original location, but the phase factor can increase by 2 pi because phase 2 pi is equivalent to it. So if you do this kind of gauge transformation, you can move from 0 flux Hamiltonian to 2 pi flux Hamiltonian. And even on the lattice model, you can define this large gauge transformation. So the large gauge transformation is a name for this kind of non-trivial gauge transformation. And yeah, if you have lattice model like a Hubbard model, the gauge transformation, large gauge transformation can be written like this explicitly. Okay. So yeah, in this view, the adiabatic insertion of random bone flux can be formulated in this way. So first, we increase the random bone flux inside this link from 0 to 2 pi. Then you do this adiabatically. Then generally, this wave function may change from psi 0 to psi 0 prime. But you cannot directly compare this final state wave function with the initial state wave function because the final state is for Hamiltonian with 2 pi flux, but the initial state is Hamiltonian for Hamiltonian with 0 flux. So you are in a different case. So in order to compare the initial state with final state, you must apply this large gauge transformation to the final state because by the large gauge transformation, you can go back to the original gauge where vector potential is zero. So you start from the initial state, let's say ground state, for example, then adiabatically increase the flux, then you evolve into some other state, psi zero prime. But then in order to compare with the initial state, you must apply this large gauge transformation. So you must compare this state with psi zero. So that's one background. But I also want to point out that even though Arnold-Bohm effect is really quantum mechanical, and classically you cannot detect the flux inside by particles moving around in this blue region. But that's only true for static case. So if you increase this flux in time-dependent manner, even adiabatically, actually you increase the vector potential in x direction, in blue region, which means that you induce electric field by this such change of the flux. Yeah, so this is of course high school physics or something like that. But if you change the flux inside this ring, then you are actually inducing the electric field in x direction. And this is true for either for classical or quantum system. So what I want to do is to, at least in theorist Gedanken experiment, I increase this flux, then I can generate this uniform electric field in x direction. Then I want to study the response of this system electrons to this uniform electric field. So now with this setup, I want to formulate the Drude weight in alternative way. That is, yeah, in the beginning I introduced the Drude weight for linear conductivity, which is kind of standard in textbooks. And usually in textbooks, this Drude weight is defined as a coefficient of this delta function, like a 1 over omega singularity at omega equals to 0. That's perfectly fine. That's correct. But alternatively, we can think of Drude weights in terms of real time. So we can formulate a linear response theory in real time. That is, current at time t is induced as a response to the applied electric field. But generally, the effect of electric field can accumulate, and electric field applied at time t prime can affect the current at time t, as long as t is bigger than t prime. That is, there is a causality. The electric field applied at particular time t prime cannot affect the current in the past, but this electric field can affect the current in the future. So generally speaking, the linear response theory for this current can be written like this. That is, current at t is given by integral of the effect of the electric field in the past. You integrate over t prime from minus infinity to time t. So this is now a real-time response function for the current. And this argument of sigma corresponds to the delay between the applied electric field and actually induced current. And this real-time response function can take, in general, many different forms. But what corresponds to Drude weight in this real-time formulation is that this sigma is a function of delay time t, and you take the limit t goes to infinity, and this limit is nothing but Drude weight. So in terms of real time, the meaning of Drude weight is that you apply the electric field. Then this electric field can affect the current in the future. But you might expect that if you apply electric field and wait for a long time, then effect of electric field would vanish. Okay, that's true for insulator. But if you have perfect conductor, once you apply the electric field, you accelerate electrons. And this motion does not completely decay. And even after infinitely long time, there is some current still flowing. And how much current is still flowing after infinitely long time is nothing but the Drude weight. So in order to formulate this Drude weight in this way, let's say I start from the ground state. Let's say we consider zero temperature, then initial state is given by ground state at t equals 0. Then I switch on a constant electric field after t equals 0. So this can be realized by increasing the Aharonov flux linearly in time, or equivalently increasing this vector potential Ax proportional to this time t. And I apply electric field for a certain length of the time, which is capital T. Then this calligraphic A is kind of final value of vector potential. And when time reaches this capital T, you reach this final value of vector potential. If you do this, magnitude of this electric field is given by calligraphic A divided by length of the electric field pulse T. Then I consider adiabatic. This capital T goes to infinity. So in this adiabatic limit, I'm only interested in very long time response of current to the electric field, which means that I can forget about the short-term response, and I can focus on this long-term response, which is nothing but the Drude weight. So I can replace this current at time t by this Drude weight times this vector potential for large t. And this can be useful because of the following observation. So what is current operator? So in general, the current operator is defined by derivative of Hamiltonian with respect to the vector potential. Then current density, to obtain the current density, you need to normalize by volume of the system or something. But anyway, the current is proportional to the derivative of Hamiltonian with respect to the vector potential. But in my process, I'm increasing the flux of vector potential linearly in time. So that means that you can replace, for this particular process, you can replace the derivative with respect to vector potential by derivative by time with some normalization factor. Then you take the expectation value of both sides and then integrate from 0 to capital T, that is from initial state to final state. Then what happens is that on the left-hand side, you just integrate the current. But on the right-hand side, you integrate this time derivative of Hamiltonian, then take expectation. Then this time derivative of Hamiltonian integrated over time is equal to the energy increase during this process. Starting from the initial state, you apply the electric field pulse to over a very long time period. But anyway, from initial state to final state, in general, the state changes. Then energy can increase. So on the right-hand side, you obtain this energy increase during this flux insertion process. On the other hand, on the left-hand side, you have integration over current from t equals 0 to capital T. But as I said, when you consider adiabatic process, you can replace this current by Drude weight times vector potential. Then you can do this integration explicitly. Then you obtain some Drude weight times some factor. So now you can compare left-hand side and right-hand side. Then you find that Drude weight must be proportional to the energy increase. The energy increase of the ground state due to this vector potential. So we have this formula. But now the ground state energy can be regarded as a function of flux or function of vector potential. And for very large system, this vector potential becomes very small. So you can replace this formula by this formula, that is Drude weight is given by second order derivative of the ground state energy with respect to the vector potential. And let's say set vector potential there. And this is actually nothing but the famous Kohn formula, which was derived by Walter Kohn back in 1964. So this is very, very known formula. But I just, perhaps his derivation was essentially same as what I argued maybe. But anyway, this is just a de-derivation of the famous Kohn formula for the Drude. So you might wonder what's the advantage of this real-time formulation and flux insertion. The answer is that actually we can now straightforwardly generalize this result to nonlinear conductivity. Because in real time, I can also formulate the nonlinear response in this way. So current at time t is given by summation on the integration over all the effects of the electric fields applied in the past. For example, the nth order term involves n electric fields at time t1, t2, time tn. Then there is a response function, nth order response function with delay time t minus t1, t minus t2, up to t minus tn. And you have to integrate over t1, t2, tn. Similar way. And we can generalize the concept of Drude weight to this nonlinear conductivity, like in the linear conductivity as follows. So Drude weight, higher order Drude weight is just a limit of this higher order response function in the limit of infinite delay time. So you apply electric field in the past and wait for very, very long time, infinitely long time, and there are still second order, third order effects you can observe in the current, and that defines the higher order. At least this is our definition. Then now I can use the same trick because current operator is always given by derivative of Hamiltonian with respect to the vector potential, and the vector potential is proportional to the time. So I can replace I can identify the current with the time derivative of Hamiltonian. Then yes.
So you want to discuss only a special component in the higher rank tensor.
Right.
Yes.
Well, yeah, we generalize to X, Y, and so on, but for simplicity, I just explain about this diagonal component. We can generalize to XY like. Okay, so the logic is the same. So I can compare the energy increase during this adiabatic flux insertion with integration of the current. And the current is dominated by Drude weight for this adiabatic process. So I replace current with this formula, and so the current with this formula, and compare order by order between left-hand side and right-hand side. And it's just a simple exercise, but the final answer is this. So n soda Drude weight is given by n plus first derivative of the ground state energy with respect to the vector potential. The ground state energy is function of the vector potential. So yeah, of course, if you put n equals to 1, this reduces to a very well-known conformula. But for second order Drude weight, you need to compute a third order derivative. For third order Drude weight, you compute a fourth order derivative and so on. So yeah, it's very compact. The final expression is very compact. And this is our generalization of conformula to nonlinear Drude weight. So this is one side order story. But with this real time formulation, we can also consider the other limits. Yes.
Could I ask a more conceptual question?
Yeah.
Which is, when Drude weight equals 0, you might call it an insulator. But suppose that the Drude weight is 0, but there's a D2 is now 0. What would happen? Is it like becomes some sort of conductor again, or?
Yeah, that's a good question. Yeah, first. Yeah. Okay, good question. Yeah, okay. So the short answer is I don't know yet, but maybe the related. Yeah, okay. So maybe one related subject is that Oka-san, who is here today, maybe, but he studied so-called electric breakdown effect using the similar setting. And electric breakdown means that you have insulator, but you apply electric field, and when electric field becomes strong enough, this insulator breaks down and starts conducting the current. And actually, I'm not.
Yeah, but it's not only the possibility. So in many cases, the regular part of the linear conductivity can have a finite value in the limit of the So then, in that sense, it's a method, right?
Okay, that's a separate question, I guess. So
and in real models.
Yeah, so in real material, yeah. Yes.
Model even in model it happens later.
Yeah. So I think these are two, of course, kind of related, but separate issue. So about if linear Drude weight vanishes, but if higher order Drude weight is non-zero, should we call it conductor or not? Maybe it's a matter of definition, but maybe it's also kind of related to electric breakdown, although maybe it's non-perturbative. I forgot, but okay. That's,
but the electric breakdown is not this type of.
Yeah, maybe it's singular, yeah, exponential, yeah, okay. But in principle, we can. Okay, I don't know exactly.
From the experimental side, that even the n equal 1 equals 3, and the d1 equals 0, but for example, the ferroelectrics almost always have the d2 term. Yeah, that's they call shift, right? Yeah, and that's called insulator from the experiments.
Yeah, so maybe to some extent it's matter of division, but yeah, I think we want to study more examples. So this is just a kind of general information. So what happens in real systems I want to investigate. And Concerning Zetsu-san's question, yeah, that's also important, but it's separate issue that
Yeah,
is
but
even.
I think usual result is the case. The omega, the Drude, theoretical Drude.
Yeah, yeah,
So,
broader,
the data
yeah.
part has some peak.
Yeah, in realistic model, yeah.
So then it's a method. So therefore, the non-zero value of Drude rate defines if the system is better or is too much.
Well, yeah, so I would say, yeah, this Drude weight characterizes so-called perfect conductor, which is different from superconductor, but kind of somewhere in between the regular metal and the superconductor.
Yeah.
And,
But perfect conductor is different from beta.
yeah, so maybe I should say perfect. Although maybe in original paper by Wotacon, he was saying metal versus insulator, conductor versus insulator. Okay, so that's really not completely correct classification. I agree. So okay, so another advantage of my real-time formulation, at least for me, is that we can also naturally consider the other limit. That is, previously I considered adiabatic insertion flux. So taking a very, very long time or infinitely long time to insert a flux. But you can also consider sudden insertion. That is, you start from zero flux and suddenly switch on the flux. And yeah. So that can be formulated using the same linear increase of the vector potential, but by taking this time capital T to zero. This limit this becomes a sudden insertion. And physically this corresponds to delta function electric field path. So this is like a standard exercise in quantum mechanics that Hamiltonian changes because Hamiltonian had the flux initially, but after switching on the flux, Hamiltonian has non-zero. So it's like a quantum potential suddenly changing the Hamiltonian. But in this limit, so if you look up Landau's quantum mechanics or whatever, the quantum state or wave function cannot follow the change of the Hamiltonian. So the wave function remains the same, but the Hamiltonian changes. But one subtlety of this problem is that, again, so if you insert unit flux quantum, the wave function does not change by inserting the flux, but you move to the different gauge. So in order to really compare initial state with final state, you need to apply this large gauge transformation. So even though this insertion of flux is sudden, after this large gauge transformation, the final state wave function can be different from the initial state wave function. Yeah. Anyway, so that means that the energy can increase by sudden insertion of the flux. But also in this limit, we can use the same trick. Current is given by time derivative of Hamiltonian. Then you integrate both sides. Then on one side, you obtain the energy increase due to now sudden insertion of flux. But on the right-hand side, you integrate over current from 0 to capital T. But now I'm considering the limit, capital T goes to 0. So this integral is also over a very short period of time. In that case, basically this current only reflects the instantaneous response to the electric field because any effect cannot appear here because this time period is very, very short. So you can replace this current by some instantaneous response with 0 delay time times some vector potential. And then you can integrate this term explicitly. Then compare order by order. And on the other hand, this energy increase due to sudden flux insertion is simply given by ground state expectation value of the new Hamiltonian after inserting flux minus original Hamiltonian. So the expectation value of first term is energy after inserting the flux, and the expectation value of the second term is just original ground state energy. Then you subtract. And interestingly, this difference is exactly the same thing as what appears in original proof of Lipschutz matrix theorem. So this is for people who are familiar with Lipschutz matrix theorem. And if you are not familiar with, you can forget about this. But if you have seen the original proof of Lipschutz matrix theorem, this is nothing but the variation energy appearing here.
This series seems to be divergent, right? Because T goes to 0, and then the sigma n, high order sigma n seems to contribute exponentially more.
You are asking
Yeah,
about it. Well, you integrate over this small t to n's power from 0 to t. So actually, this capital T cancels eventually. Yeah.
Okay. Yeah.
Yeah. So anyway, so now this energy increase. So the logic is exactly the same as in the adiabatic limit, but the actual value of energy increase is different. And in this case, it's given by this difference in the expectation value. So to summarize, and the result of comparing order by order between left-hand side and the right-hand side, what we obtain is this formula. That is instantaneous response of the current to the electric field in real time. Nth order is given by the ground state expectation value of n plus first derivative Hamiltonian with respect to the vector potential. Okay. So this is a formula, but what is the instantaneous response in real time in frequency space is that you just consider the nonlinear conductivity as a function of frequencies, n frequencies, and if you integrate over all the frequencies, then you can recover the instantaneous response in real time. So this actually corresponds to another famous result in linear response theory, that is so-called F sum rule or frequency sum rule. So if you set n equals to 1, this is just a linear conductivity, AC conductivity integrated over all the frequencies. And this is given by expectation value of second order derivative Hamiltonian. But this is, again, naturally generalized to higher order nonlinear conductivity. So this is a nonlinear generalization of F sum rule. And as you have seen, although Drude weight and F sum rule look very different subjects, in this way, it can be formulated in a unified way. The Drude weight corresponds to adiabatic insertion, responds to the adiabatic insertion, and the F sum rule corresponds to response to the sudden insertion of the AB flux. So yeah, we also studied this off-diagonal component. Yeah, I'm running out of time, so Steve. And, okay, so we did some numerical check our nonlinear Drude weight and F sum rule seems to work. And yeah, let me touch briefly. So now we have nonlinear, the Kohn formula for nonlinear Drude weight. It should be interesting to apply that formula for interacting system, for example, spin 1/2 XXZ chain. So this is a spin chain, but the equivalent to free fermion model, spinless fermion model with nearest neighbor interaction. Nearest neighbor interaction. So you can define the Drude weight, linear and nonlinear for this XXZ chain. And this is particularly interesting because it's well known, but this model is exactly solvable by a so-called Bethe-Anders technique. And the low energy limit can be described by field theory, thermodynamic. So there are a lot of technical, theoretical tools to study this. And in fact, by combining the Bethe-Anders and field theory method, so there is a remarkable paper by Luciano, a real expert on this Bethe-Anders field theory business. And there is an old paper back in 1998 by Luciano. And if you look up his paper, old paper, then we can extract this higher order Drude weight using result in his paper. And this is the exact expression for third order Drude weight in XXE model. And the delta is the anisotropy parameter in XX chain or interaction strength. And the delta is parameterized by gamma, then third order Drude weight is given like this gamma function ratio. And this formula agrees well with some numerical calculation. So it seems to work. But what is strange is that, okay, so here this third order Drude weight remains finite, but actually for delta less than -1/2, at delta equals to -1/2, this Drude weight, third order Drude weight seems to diverge. And below this delta equals to -1/2, it seems to be divergent. So that's kind of strange. But yeah, later our result was extended by Katsura-san group. These people, and they computed the fifth order Drude weight, which has even more complicated form. But and again, it agrees with numerical calculation. But now this diverges for delta less than 0. So the region of divergence increases as you go to higher and higher order. So this sounds strange. So we try to understand why this diverges and what it means physically. So for this purpose, we studied a very, very simple model of just 1D free electron with single impurity. Okay, so this is like what you saw in undergraduate quantum mechanics. But this is, of course, exactly so. That's why it's used for our purpose. And we can apply this nonlinear Kohn formula to this simple system and calculate almost everything exactly. Then result is that actually the Kohn formula, Drude weight according to the Kohn formula also diverges for this very, very simple model. Although in the bulk, there is nothing. So, so from this simple model, even for this very simple impurity model, Drude weight diverges according to the Kohn formula. And our conclusion is that this is related to the order of limit. That is, when you apply Kohn formula, you start from finite size system, and you need to take really adiabatic limit for given system size. So that means that if you are using Kohn formula, you are first taking the adiabatic limit or omega 0 limit first. Then after that, you might consider some line limit, L goes to system size, L goes to infinity. And so this limit, we propose to distinguish by calling this limit as Kohn-Drude limit. But if you are really interested in bulk property, bulk transport property, then this may not be so physical limit. Because if you are interested in bulk property, then you must first take some time limit, fixing some time scale or frequency. And after taking some time limit, you take adiabatic limit. And this limit can give different value than this limit of Kohn formula. And we propose to call this alternative limit as order of limit as a bulk Drude weight. And advantage of our model is that because it's a single impurity, very simple model, we can explicitly calculate this bulk Drude weight by, so for example, this linear conductivity as a function of frequency, and at zero frequency, there is a large delta function like a contribution. And if you use Kohn formula, you only pick up singularity at exactly zero frequency. But for finite size system, there are also other low energy contributions like this. And for example, this red curve is for system size 22, and the blue curves are system size 42, and the green for 62. And you can see that there are low energy peaks, low frequency peaks, which behaves like, which appears as at the frequency roughly 1/L. So these low energy peaks merge to zero frequency in the thermodynamic. But if you use Kohn formula, you ignore those low frequency contributions, and you only pick up strictly zero frequency peak. So in order to include those low energy, low frequency peaks, we can first define the integration of frequency from minus capital omega to plus capital omega, include those low energy peaks. Then first take the thermodynamic, at least in place. Then afterwards, we can take this omega. Of course, in practice, it's not so easy to do, but for this simple impurity model, we can kind of estimate. So for example, this is a result for linear Drude weight. So if you use Kohn formula, you find this kind of curve. And this horizontal axis is Arnold-Bohm flux. So the Kohn formula depends very strongly on Arnold-Bohm flux. But if you think about it, if you are interested in a bulk property of the system, the bulk property shouldn't depend on Arnold-Bohm flux. So instead of this Kohn formula, if you include those low frequency contribution, then what you find is almost flat straight line, which means that this corresponds to bulk Drude weight. And the bulk Drude weight actually does not depend on Arnold-Bohm flux, and actually doesn't depend on impurity strength, because this is really looking at the bulk. So yeah, we can recover the so in some sense, this Kohn formula shows some pathological properties, which is not really related to the bulk property. But concerning this bulk Drude weight limit, we can recover expected simple bulk physical. And that is for linear Drude weight, but we can play the same game for nonlinear conductivities, which are functions of two frequency. For example, the second order conductivity is a function of two frequency, but in frequency space, there are a lot of structures. And again, you can try to include low frequency contributions. And again, this is a second order Drude weight. Again, the second order Kohn formula shows very strong dependence on the Arnold-Bohm flux. And moreover, this is for system size 22, and this is for 102. So system size is very different, but the curves are similar. But here, actually, we are plotting is a Kohn Drude weight like object divided by system size. So they look similar, means that this Kohn Drude weight is diverging as you increase the system size. But if you include those low frequency contributions, then this result is this green line, which is actually basically vanishing. And this is actually what is expected, because in the bulk, here we only consider the tight binding model. So there is nothing breaks the inversion symmetry. So in the presence of inversion symmetry, the second order conductivity should vanish. So second order Drude weight should vanish. But if you use Kohn formula, then actually it's diverging and also depends on iron bond flux. But if you include low frequency contributions and compute the bulk Drude weight, it vanishes as physically.
Sorry.
Yes.
Are you saying that this divergency is sort of unphysical?
Yeah, in a sense, yeah.
So basically, all these previous calculation with bad answers should be wrong.
Well, yeah. For the bulk properties, wrong. But still, one question is, in some region of parameter, it does not diverge. So in that case, I still conjecture that the Kohn formula gives a correct bulk limit. But of course, there is no guarantee. So in order to answer that question, so this divergence is in a sense unphysical. I agree, yes. But when this Kohn formula gives a finite result, does it agree with this bulk limit or not? That's a non-trivial question, which I don't know the answer. Yeah, for that, we really need to take this bulk through the weight limit for interacting system, but that's much more difficult. But conceptually, yeah, we should consider that. Okay, so I'm running over time, but to summarize, okay, at least as a general formula, we have two nice formulas. So F-sum rules and Kohn formulas, and both can be generalized very naturally to nonlinear responses. And actually, the formulas are quite similar, but actually different. And this difference corresponds to different limit of this flux insertion. So F-sum rule can be derived by considering sudden insertion of flux. And on the other hand, the Drude weight Kohn formulas can be derived by considering the same flux insertion process, but instead of sudden insertion, you consider adiabatic insertion. Then you obtain this. And at this point, everything looks clean and nice. But if you try to compute this Kohn formula actually, then you can find a lot of pathological results. And this pathology is related to the this order of limit business. So we argue that in order to really study bulk transport property, you need to take the sound limit first at some fixed frequency or time scale. Then after that, take the adiabatic limit, which corresponds to very long time electric field pulse, or take zero frequency after taking sound line. And we actually did this for very simple impurity model of free electrons. But of course, we should also do this for interacting system like XXE, but that's very difficult problem. So at this point, we don't have any concrete result. And actually, when we look at the literature of the linear response, this importance of this order of limit is mentioned in some literature, but as far as I know, the difference has not been so much worked out. And also, in linear Drude weight, there is no divergence. If you consider nonlinear Drude weight, then sometimes the Kohn formula diverges. So the difference due to this order of limit, different order of limit is kind of amplified in case of nonlinear response and nonlinear Drude weight. So that also gives some hint to understand linear response. Okay, yeah, that's what I wanted to say. Yeah, thanks for your attention. Yeah, and so this is related to the question by Tsunetsu-san near the beginning of my talk. So, and also this level costing business. So if you consider strictly adiabatic process, then even when there is a very, very tiny level, you always follow the low energy branch. But in order to consider this bulk Drude weight limit, actually you need to keep the finite sweeping speed. So sometimes you actually jump over very small level of diversion. But yeah.
I don't understand why is the artificial divergence doesn't appear in response. I understand that there should be something like that.
Well, yeah, okay.
But what doesn't matter?
Well, so that's also, yeah, maybe appearing here. Okay, so in general, ground state energy is function of system size and the Aharon flux. Okay, so now the symbol is different, but here theta is the Aharon flux. Then you can expand the ground state energy like this way. So first term is the ground state energy density times system size. And the next term is some constant. And the next term is the 1 over system size and so on and so on. Then we can okay, but actually flux depend this first term does not depend on the flux because this is the ground state energy density. So it's insensitive of flux. And also this constant term is basically defect energy. So some extra energy due to defect. So this also does not depend on the Aharon flux. So the Aharon flux dependence actually starts from this term, the coefficient of 1 over system size term. So we can define the nth order derivative of this term, like a dA.
But the current is it's a 1D system.
Yeah.
But how about the case for three-dimensional systems? Then the theta dependence should appear already in the term which is proportional to system size, right?
Okay, yeah, because if we consider L by L by L,
Yeah.
then everything is multiplied by L squared or something. Yeah. Okay, so
1D is very special.
yeah, in some sense maybe, but so far this divergence and so on, we only observed in 1D. Okay, so for higher D maybe we have to think about this. Okay, so this is for 1D system, but what I wanted to say is that this nth order Drude weight in cone Drude weight, like object, is proportional to this derivative of this coefficient with respect to Aharon flux. But you multiply with this system size to power of n minus 1. So if you consider linear response, n is 1. So there is no factor. This is just order 1 factor. So this is finite, then this is finite. But if you consider higher order cone Drude weight, you have this factor of L to some positive power. And this is just a source of divergence. So in this sense, if there is some dependence of this coefficient on Aharon flux, generically we can expect the divergence. Yeah, this is mathematical.
I got a different question. You said that you want to characterize the perfect conductor using the Drude.
Yes.
But the other definition of D cannot distinguish perfect conductor and superconductor.
Right. So actually, yeah, Drude weight, if I remember correctly,
It's non-various and legal.
yeah. So Drude weight just gives you lower bound for the superfluid density.
Yes.
So having non-zero Drude weight is okay. No. Drude weight is sorry, upper bound of superfluid density.
Yeah,
So-
what? Something is missing or? I think that gives the exact values of Drude in superconductor.
Good question. Yeah, okay. I forgot the answer. So there's a famous Scalapino white jump paper. They discussed the relation between Drude weight and superfluid density. Well, those again are related to different order limits. I think. So the Drude weight is related to
Maybe they are discussing the limit of K equals.
yeah. No, yeah.
It's a difference.
Yeah. But I was saying that in their framework, superfluid density is related to omega zero limit first before Q zero limit. So keep Q finite.
If you change the order, you get the orbital stability.
Yeah. So Drude weight versus superfluid density is related to different order limits between omega zero and Q equals zero, at least according to their framework. But it's okay. It's a bit similar, but here system size versus omega zero.
I think it's exactly what I want this.
Sometimes I forgot, but at least in some cases, I think you're right. This superfluid density for, let's say, attractive Hubble model, probably should equal to the weight. So under some condition, this inequality becomes equality. Superfluid density. Sorry, I forgot under what condition. Yeah.
I wonder if what you are calculating right now is about kind of zero temperature.
In my talk for simplicity, I focus on zero temperature limit, but
so is it obvious how one can do it for finite temperature?
Yeah, well, at least formally we can do the same thing. So I think this this you can replace by just a finite temperature trace of this object with density matrix. And this also can be generalized to finite temperature by
it couldn't be E naught.
So this is an En derivative of nth energy eigenvalue and multiplied by boson weight for nth.
Okay.
At least formally we can generalize, but again, this order limit issue also applied to finite temperature.
And then I have a kind of follow-up question that one can calculate, for example, the Drude weight using some kind of Mazur bound or something like that. So could one do something similar for the nonlinear one?
Yeah, that's a good question. That's actually deriving some bound for nonlinear Drude weight is one thing I'm trying to do now. So I don't know the answer yet.
Okay.
But actually that's important for practical purpose because for linear conductivity, F-sum rule has been very useful, for example, to check some numerical computation. You do some numerical calculation for conductivity and compare with F-sum rule. That was particularly useful because for linear conductivity, this sigma or omega is non-negative. It's zero or positive. So that means that if you can numerically compute sigma or omega over some finite window of frequency space, then compute the integral of sigma or omega. But that should be less than F-sum given by this F-sum rule because the sigma or omega must be non-negative. But for nonlinear responses, nonlinear conductivity, the sigma of omega 1, omega 2, for example, can be negative or positive. That means that the F-sum rule formally holds. So this should be hold, and this you can replace with frequency integral. But because the sigma can be positive or negative, if you numerically compute sigma of omega 1, omega 2 over some finite range of frequency, you don't know whether this is bigger or smaller than F-sum. So this is kind of, for me, nice result, but the practical utility is still limited because of this. So I want to derive some more inequality type stuff which can be more practical, but I still don't have this happening.
So in that sense, the negative value of E3 is harmful or not, physically? Isn't there any catastrophe?
Well, yeah, so far, no, yeah, so
Yeah, for example, the existence of the very tiny value of linear Drude is a very large negative value of nonlinear Drude. Is possible?
well, so I don't know enough yet to really answer your question, but as far as we see from some concrete models, this divergent higher order Drude weight does not really mean diverging current. For example, we can do real-time simulation. And then in real time, current may be increasing or decreasing, but this diverging Drude weight does not really mean.
Yeah, but I'm worried about the relative result.
Oh, yeah. So
It seems that the stationary current is going into the opposite direction of that large field.
yeah. So that, yeah, when that can happen when you have this level crossing and the level reversion, then by increasing the vector potential, you first increase the energy. And this corresponds to positive current because of this relation between Hamiltonian derivative and current. But if you have level reversion and if you follow the lower branch, then under adiabatic insertion flux, energy first increases, but after this level reversion, the energy starts to decrease. And this decrease of energy should correspond to backflow of the current or something like that.
You say there's anyways, the voltage drop is zero, so related to the current, so it doesn't matter. I'm talking about something like a heat production.
Oh, okay. Well, yeah, in this formula, yeah, I'm not sure how. Yeah, maybe heat production only occurs in heat bars or something, but yeah, anyway, so this negative Drude weight is related to energy decreasing as a function of a vector.
I'm not asking about the formulation.
Okay. Physical.
Physics.
Uh,
Such a kind of behavior is allowed, possible, theoretically, conceptually.
well, yeah, when you have level reversion, if you know,
But there's always heat in nature.
well, maybe just yeah, maybe this battery is giving positive energy to the system or extract energy from the system. I guess at this level it's just energy is given to the system by the battery, this external apparatus, or external apparatus is extracting the energy from the system, something like that. But yeah, this heat production kind of question is should be important. I'm trying to understand that. At this point, I don't have too much to say. Yeah, thank you.
Can I comment on that?
Thanks. Yeah.
Do you hear me?
Yeah, we can hear.
Good. Sorry, I'm outside, so maybe I'm not speaking well now, but so decrease of current is, I think in our understanding that is related to Bloch oscillation. So the current increases at first, and it decreases after some point, right?
Yeah.
So the question was like the meaning of like negative value of linear Drude weight or non-linear Drude weight. I didn't quite get.
Yeah, he's asking about nonlinear.
Non-linear one. Yeah. Okay. So I think that happens even in the non-interacting model, right? Even without infinity, like just the most basic like nearest neighbor type model.
Yeah.
So I think that is related to the Bloch. I mean, the understanding of the Bloch oscillation is really coming from that negative value. It just means like on the lattice, current just oscillate, even if you apply a constant electric field, right?
It's oscillate with finite frequency. And then you are talking about this omega equals 0 response.
Yeah, so you say that whenever the DC voltage increases, then we are in that case. In my opinion, some non-linear response can be zero, but the total current should be positive.
So that's why I asked is it's possible to use the small value of the positive linear and the large negative value.
Yeah. So that's yeah. For example, the total equation of the current should be positive.
Yeah, that is my feeling.
No, not only feeling. That should be.
But I asked it that can be his formulation.
Actually, I'm trying to figure out that kind of question now. I don't have good answer yet. Thank you.
You need to sum up. You should consider all the orders, right?
Yeah.
Just order is negative. You cannot stop.
Yes.
So
So in that sense, maybe in this formula we separate each order of response separately, but maybe more meaningful quantities like a total current. Yeah, I tend to agree.
Yeah. Also, like I want to come back to the the discussion about superfluid density and Drude weight.
Yeah, please.
I think if I remember correctly, like the Scalapino Zhang white paper.
Yeah.
So they computed response of X component of current toward say like a gauge field applied in AX component of the gauge field. So that's like a XX component, right?
Yeah.
And then like when they compute superfluid weight, right? So they set omega equals 0 first, and QX and QZ equals 0.
Yeah.
And they keep QY finite, right? Y component finite. And take the limit QY goes to 0 at the end of the calculation. So like you need two special at least like you have to work in the two special dimension, and you compute XX component of the response function, and you set momentum other than X to be finite, and take that value goes to 0. That's the calculation for superfluid density.
Okay.
But in our calculation, like in our 1D model, we have only one special component.
Yeah, right.
Yeah. So like in this calculation, like we are computing X component of the response function, and set QX finite, and let QX goes to 0. That kind of limit is what we are computing, I think.
Yeah. Thanks for reminding. Yeah, I studied this Scalapino by Zhang paper many years ago, but I kind of forgot.
Yeah, I recall. The supercurrent density is defined for thermal equilibrium. That is a.
Yeah.
So therefore, the omega should be 0 first. Yeah.
Other comments or questions also from Zoom audience? Okay. Yeah, if not, thanks for joining. 渡辺君、thank you.
すいません、今子供の迎えててちょっともうなんか 全然議論に